Hey, greetings, good day, and welcome to exam 2B! Or not 2B. No, this is decidedly 2B. Let's do it. Here is the question. Number 1. We need to identify the acid, base, conjugate acid, and conjugate base in this reaction. So, what we're looking for is the proton transfer. So notice how this molecule, specifically at this nitrogen, in the course of the reaction, gained an H+. This means that this chemical species must be our base. So, the thing that lost the H+, in this case, the water, well, the proton donor is our acid. So now that we've identified our base and our acid, identifying their conjugates is really straightforward. The base becomes the conjugate acid, and the acid becomes the conjugate base. So it's choice E. In this problem, we're given the free energy change of the entire reaction, and we're given the free energy of formation of a few of our molecules, our carbon dioxide and our water, and we're looking for the free energy of formation of glucose. Now, wait a minute. Anytime we want to relate the free energies of formation with the free energy change of the reaction, we can use the products minus reactants rule, as indicated here. But we're not given the free energy of formation of O2 gas. Or are we? O2 gas is in its standard elemental state, which means its free energy of formation, just like its enthalpy of formation, is, drum roll, 0. So we have all the information we need to solve for the free energy of formation of solid glucose. So we have our delta G, standard of the reaction, is equal to the sum of the free energies of formation of the products. So 6 times the negative 394.4 kilojoules per mole for the CO2, plus 6 times the negative 237.2 kilojoules per mole for the water. So those are our products, minus the free energies of formation of our reactants. The free energy of formation of glucose, which is what we're solving for, plus 6 times the free energy of formation of oxygen gas, which again is just zilch. So, let's solve for our delta G standard formation of glucose. So we have the delta G standard change of the reactions, negative 2,879 kilojoules per mole, equals negative 3,789.6 kilojoules per mole. Sorry, I should have put the units in there. Plus the delta G standard formation of the glucose, which we're solving for. So subtract the negative 3,789.6 from both sides, and we'll get, oops, sorry, really quick to make a correction. Sorry. Put a plus here. That's not right. It's supposed to be a minus. So I'm going to correct that quickly. Sorry about that. Negative 910.6 kilojoules per mole. Okay, so once again, we're given information about the molecules involved in a reaction, and we're looking to find out the overall, in this case, entropy change. So since we're given the absolute entropies of all these molecules, we want to find the overall entropy change of the reaction, we have to once again use the products minus reactants rule. So, let's set it up. So our standard entropy change for this reaction is going to be equal to our products, 4 times the standard entropy of carbon dioxide, 213.7 joules per mole Kelvin, plus 2 times water's standard entropy, minus the reactants. And then I highly recommend not being a calculator superhero here and just doing, calculating the total entropy, the sum of the entropies of the products and the sum of the entropies of the reactants independently. So here we have the sum of the entropy of the products minus 1,427 joules per mole Kelvin. And let's see what we get for our total entropy change of the reaction. Negative 195 joules per mole Kelvin. In this problem, we need to manipulate these KEQs to get a KEQ for this reaction right here. So these are kind of fun. They're kind of like puzzles. The first thing I always do is I check to see if in the reactions that we're given the equilibrium constants for, if the reactants and products align with where the reactants and products are in the overall reaction that we're looking for. So when we do that, we can see here in this first reaction, the SO3 is in the reactants, whereas in the reaction that we're looking for, the SO3 is in the products. So that's a good indicator that we'll probably have to flip this first reaction. So let's do just that. Whoop-pow! Here is our flipped reaction. And remember, whenever we reverse a reaction, what do we have to do to the equilibrium constant? Just going to call this Kc prime. It's going to be equal to, boom, the inverse of our original K. So we're going to do 1 divided by 2.3 times 10 to the negative 7th, and we'll get 4.3 times 10 to the 6th. But wait, our puzzle isn't over yet. So how can we get this overall reaction that we're looking for here? Well, so let's combine our flipped reaction 1 with our reaction 2. And when we do, what cancels out? Well, the O2 cancels out. And then we can get an overall reaction. So we'll get this overall reaction. And our K for this will be Kc double prime. Remember, anytime you combine two reactions together, the way that you get the new equilibrium constant is by multiplying the two KEQs together. So when we do, we'll get the KEQ for our new reaction is 6.1 times 10 to the 3rd. And we are so very close. But does our equation that we have now, our reaction, match the overall reaction that we're looking for up here? And the answer is no! But we're close. Reactants are on the correct side, products are on the right side. What's the only problem? Our coefficients. Everything here is twice as much as everything in the reaction we're looking for. So we need to cut this all in half. So if we're cutting the coefficients in half, aka multiplying the coefficients by 1/2, what happens to our KEQ? We have to take it to the power of whatever we change the coefficients by. In this case, the 1/2. And we will get our answer, which is 78. Woo! In this problem, we want to relate delta G standard to the information that we're given. In this case, we're given a KEQ, and the equation to do that is this one right here. So anytime you want to relate free energy, standard free energy change of a reaction in KEQ, this is your go-to equation. So we have delta G standard of the reaction equals negative gas constant R, 0.008314 kilojoules per mole Kelvin, times our temperature, 298 K, times the natural log of 5 times 10 to the 8th. So we will get delta G standard of the reaction equals negative 49.6 kilojoules per mole, which is choice D. Random, misplaced, decimal point, and all.